Hello, everyone. Good afternoon. So I'm Shruti Kulkarni, research scientist at the Oak Ridge National Lab. And as part of the AI speaker series at Argonne National Lab, I'll be presenting some of the broad overview of AI applications with neuromorphic computing, some from the broader neuromorphic computing community across the world, and mostly from our neuromorphic computing group at Oak Ridge National Lab. So yeah, quick background that Dennis already went over. So I'm currently a research scientist at ORNL, and previously I was a postdoc at the same lab. And my research areas, as he mentioned, span different aspects of neuromorphic computing. And as part of my PhD, I was also part of a SRC funded project at NJIT, which included studying some of the non-volatile memories and non-von Neumann architectures for accelerating SNN simulation. And I also have a couple of internship experiences at Texas Instruments and Micron, both in the domain of machine learning and hardware optimization. So here's a quick overview of my talk that I'll be giving today. Let me begin by introducing, what is neuromorphic computing and why do we need, what's the motivation behind neuromorphic computing? So the term itself suggests that it's basically a kind of computing which is inspired by the human brain. And one of the prime reasons why, main motivations behind this is, if you look at the scale of operations that our brains can perform and, what a supercomputer can, they're almost on the same orders of magnitude. But however, when we look at the power consumption, you see a drastic, 6 orders of magnitude difference over there. So the reasons behind this are postulated to be mainly by the event-driven computation that happens in the brain. That is, the data that is communicated between the neurons is sort of binary in nature. And the other most important factor is the co-location of the memory and the processing units in the biological brain. So I'll get to these points in a bit. The main form of operation in or the main computation the main form of computation that takes place in neuromorphic computing is via what are called spiking neural networks. They're like any other neural network that you find in the machine learning domain, but the difference is that they operate on what are called the spike trains. So as you can see that as we go at different time steps, the states of these neurons, which are getting the different spike trains that are binary valued data that is coming in, they operate on these binary valued data, and the spiking neural network also outputs another set of binary valued spike streams. So as a contrast with what we know from the traditional machine learning domain, which also has what are called the artificial neural networks, the difference is that the ANNs, we just term the traditional neural networks as artificial neural networks, and the one that we use in neuromorphic computing as spiking neural networks. So as you can see that these the inputs to an ANN are these real valued signals. And the operation that takes place in a particular neuron is the weighted sum of these inputs, which means that we need to perform, a multiplication and then an addition or a MAG operation. Whereas when we look at the SNNs, we can the input that's coming in is just a binary bit stream or a binary spike stream. So it ultimately boils down to just accumulating or adding up the weights that are connected to a particular neuron, whichever one is activated at that particular time instant by the incoming spike signal. And because these spike signals are all binary, so it's just a summation operation that it boils down to. So so that's a quick introduction of what is neuromorphic computing and why do we what's the motivation behind it. Now, going on, now before I go deep into some of the applications and algorithm works at our lab, here are some of the software and the hardware platform that we have at ORNL as part of the Neuromorphic Computing group. So for the software framework, we have what is called the 10-lab neuromorphic framework, which has been developed by researchers at both as a collaborative effort between researchers at ORNL and the University of Tennessee. So this basically, because neuromorphic computing is an evolving evolving field where we do need to have a good software framework to develop different applications and algorithms. This framework basically allows us to develop different kinds of algorithms for the different applications, whether it's classification, control, or temporal data classification, and at the back end, it also provides us different hardware support for different hardware backends and also different simulators. So these that you see on the bottom left corners are the different neuromorphic hardware that the developmental hardware that the neuromorphic group at UTK has been working on, and that you see on the bottom right side of this picture are the different open source neuromorphic simulators that have been published by different neuromorphic computing groups across the world. So this particular framework provides us an easy interface for both the front-end applications and the different hardware backends. And for most of our work, we look at we primarily consider the Caspian neuromorphic hardware, which has been developed solely at Oak Ridge National Lab, and it's an FPGA-based neuromorphic hardware which also has its own software software simulator that allows us to interface with the different application APIs and allows us to encode and decode the input and the output in different spike streams, and also allows us to experiment or study the different algorithmic behavior. So one single board can, without by itself, can just can implement up to 256 neurons and roughly about 4,000 synapses, and by itself can run with just a few tens of milliwatts of power. So that's a quick introduction to the different hardware and software backends that we have. And now coming into the crux of neuromorphic computing, that is, what are the different learning mechanisms in spiking neural networks? So similar to what we have in the traditional machine learning and the artificial neural networks, where a neural network model needs to be trained, or the parameters need to be adjusted for it to learn the mapping between the different input and the output data samples. In the same way, we need to train or make the spiking neural networks learn. So for this, there are there are different mechanisms that people have proposed. One is the spike-based backpropagation, where you look at the error and then you backpropagate the error and iteratively adjust the weights of the different layers of the spiking neural networks. And this is a bit challenging because of the discontinuity in the data that is that is getting transmitted between successive layers of neurons, and also the spike streams they are spread out in a certain period of time. So we cannot directly apply the traditional backpropagation algorithm that we see in artificial neural networks. Rather, it has to be modified and approximated to account for this temporal stream of binary data. And another common popular approach, which is more inspired by the neuroscience community, is is the reservoir computing, where you have a block of spiking neurons connected with certain delays associated with them in terms of the delay that is being needed to transmit a spike from one neuron to the other, and that basically translates the input spike streams that are coming in from the input layer into a higher dimensional space, and only the readout layer or the output layer is what is trained by different traditional methods like stochastic gradient descent, um, to identify the different categories of the input classes. The third approach that people take is mapping approach. That is, you take a traditional ANN, train it for the given problem, and then modify its weights and activations so that it can be translated to a spiking neural network. And the reason the reason for this is so that this spike-based model can be implemented on a neuromorphic hardware. And the fourth approach that's more common at our group is the evolutionary computing approach, where we make use of certain evolutionary or certain genetic operators to evolve the network for a given task. And the task could be either a classification or control or a regression or any kind of a machine learning problem. So this which I'll be going into further more details in my later slides. So that's how the evolutionary optimization or evolutionary computing can operate on a spiking neural network. And the last one that we look at is again based on is again a neuroscience inspired rule, which is the local plasticity based rules. So here so this is also a neuroscience based rule where the only the weights are adjusted based on the activities of the connecting neurons. This also I'll be going into detail in my further slides. So let me now go a little further deeper into bio-inspired computing and learning. So what do we? So I talked about a spiking neural network, and they operate on the binary sets of spike streams. So internally, what happens is that you can think of a spiking neuron, as an accumulator, or as the model to be something that accumulates the incoming data. And once this incoming, the accumulated data exceeds a certain threshold, a spike is issued out of it. And there's another component to spiking neural networks, which is the synapse. And there are two parameters associated with it, which is the weight and the delay. So weight is basically by how much of this input spike needs to go into the spiking neuron, or or how much of that input spike needs to get accumulated into the spiking neuron. And the delay term basically tells us how at what after how many delay should the input should this particular spike come or arrive at this particular neuron or the postsynaptic neuron. So those are the two parameters of a synapse. And when we come to a spiking neuron, I also already mentioned about the threshold, which tells us when should this neuron spike. And there's another term that's called the leak, which defines as to how if the neuron does not receive any input spike or input data, then as seen in various biological models of neurons, the charge that has been accumulated slowly decays to its resting or a reset state. So that's what this leak parameter tells about this neuron. And now I'll talk about the learning rule, which is part of the local plasticity based learning rule, and the one that we worked on or implement or explored further was called the spike timing dependent plasticity rule, which is again a neuroscience inspired rule that roughly or a Hebbian, which was postulated by Donald Hebb, an early neuroscientist, who stated that neurons that fire together and their their connections get strengthened over time. So this is the basic principle by which we can make the whole neural network or the whole spiking neural network learn for a particular problem. And another reason that this particular rule is interesting is that it is local in nature. So when we think of a neuromorphic processor, or that is inspired by the human brain, we would like to have the neurons and the processor and the memory close by, such that there is no bottleneck between the data communication between these two entities. So that's how most of these neuromorphic processors are being architected today, and they come under the category of non-Neumann von Neumann processors. So so this particular rule is interesting in the sense that it can potentially be realized on a neuromorphic or on a non-von Neumann hardware as well, because the synaptic update, the learning that is done by updating the synaptic weight is taking place by only looking at the activities that are happening at the locally available neurons. So this is the abstract, abstract look as to how neuromorphic hardware and how the local synaptic learning rule can be implemented. So we did a couple of studies and tried it on a classification problem. And for the classification problem, we applied certain modifications to the basic the spike timing dependent plasticity rule by introducing certain supervision to it. The basic spike timing dependent plasticity, or the STDP rule, operates by looking at the precise timing of the spikes that are coming in from the input and the output neuron of a particular synapse. So the incremental update for that synaptic weight is a function of the time difference between these two, between the pre and the post synaptic spike times. So this is a most commonly used weight update kernel, which is exponentially dependent on the timing difference between the two spikes. And for our particular problem, we look at a simple two-layered network where you have for the purpose of classification, and we have labeled data associated with the input features that we are applying, and to guide this whole process so that these different neurons get specialized to the different classes of the input, we also have a supervisor signal which determines the direction at which this weight update rule needs to go in order to train the network for the whole data set. So so our final weight update is basically an accumulation of all the incremental updates for all the for all the input samples. And additionally, because we also added an additive noise term to it, which is roughly about 10% of the base, the average synaptic weight that we have in our network. And yeah, and then that also helped in and another thing that we were targeting is a low precision based hardware. So I mentioned about the Caspian hardware, where all the parameters of the network are represented in the integer format. So that's why we need to round off these incremental updates so that it can be realized onto the hardware. And because of this rounding, there are certain errors and certain certain input cases where the network would fail to train. Whereas when we added this additive noise, that helped in compensating for such failure scenarios. So so that's the basic learning rule for training the network weights. In addition to that, we also have a certain number of hyperparameters that are, mapping that cater to the different phases of the training, right from input encoding to what are the network parameters, and then the algorithm itself has a number of parameters. So we applied what is called the Bayesian optimization to uh, to train the, or to optimize these different hyperparameters of the overall network to match so that the network can predict uh, make the correct prediction for the given input classes. So so these are all listed in our last year's icons paper, like how we carried out the optimization study. And we applied this to some of the four data sets from the UCI database, which included the iris, breast cancer, wine, and digits. So so we were able to obtain very fast convergence with this simple STDP based rule, and with obviously the optimized hyperparameters that we obtained by applying the Bayesian optimization. Um, So when we compared our results with some of the other spike-based approaches that were listed in the literature, at least for the three simpler data sets of iris, breast cancer, and wine, we obtained close to the best uh, results that have been published previously. For the digits, because it is a high dimensional data set where and it's a much larger database than the other three. We weren't able to get to the best case with a simple two-layered network. So that's something that we are currently, working upon to improve the learning ability with supervised STDP for complex data sets as well. And in addition to these are all the static classification data sets that we used. And in addition to that, we also looked at some of the temporal data sets where every input sample is basically present for a certain number of time steps. One of the data sets, again from the UCI database, was the activity recognition data that we looked at. So this particular data set, again, this particular data set has basically sensory values from different points from a human body, and that data is needed to be classified into 7 different categories of the different activities that the human is performing. And each sensor value, or each of these sets of values, lasts for 120 seconds, and they're sampled at 250 millisecond duration. That means that we have about 480 time samples of these different sensory analog data samples. In order, so for us, when we tried to train, when we were training this particular sample, because each data sample just has 6 features, we tried out different encoding schemes for converting the analog values into spike strains. And we observed that when we employed a population encoding, that is every input sample gets mapped to four of the input neurons. And that basically generates different spike streams for the different analog value. So with this, this was basically carried out with some of the summer interns at our lab last year. And they observed roughly about 80% accuracy on this activity recognition data set. Again, this was with a simple 2-layered network. So this is so I think the best case accuracy is somewhere around 90% on this particular data set, but that is with a much larger network, and people have used what are called what I previously talked about, the reservoir computing approach, where you have a network where with a recurrently connected neural network, and only the readout layer is trained by stochastic gradient descent method. So this was just an attempt to study the the capabilities of the simple STDP or spike timing dependent plasticity rule for SNNs. So these are some of the bio-inspired learning applications that I talked about that we are currently pursuing at our lab. And I'll just go over some of the other cognitive applications that different research groups have also done on with some of the actual neuromorphic hardware. So here is an overview of some of the most prominent neuromorphic hardwares that are out there. So Spinnaker is the most popular one, which is an ARM-based processor, and it has been realized. It's a highly scalable supercomputer. But because it's not an ASIC, it's rather like based on these ARM processors. So compared to what you would get in say other like an ASIC based implementation, the power consumption is high, but then like there have been a lot of application demonstrations with this Spinnaker neuromorphic hardware, which was developed at the University of Manchester. And then the commercially Loihi and Intel that was developed by Intel is another neuromorphic chip. They also have that was developed. I think it came out in 2019, and they also have more. They're also upgrading it to and to increase to make it more scalable with by stacking multiple multiple or Loihi chips in order to be able to realize a very large neuromorphic platform. So I think the Poihoki platform is their latest platform, which can implement up to 100 million neurons. And then True North was one of the earliest industry-based neuromorphic hardware demonstration. This was again a crossbar-based array of neurosynaptic cores. Again, this was also like a scalable version, but the only drawback was that it could not incorporate on-chip learning. Rather, you had to have a trained network and then realize it onto the True North hardware. Then there are other analog or mixed signal based processors such as the brain scales and Dynabs that are again different university based demonstrations for neuromorphic hardware. So now just a quick overview of some of the interesting applications that people have been doing with neuromorphic computing and neuromorphic hardware. And also another thing is like they in addition to the neuromorphic the processing hardware, there are various neuromorphic sensors that are being developed in parallel. And so one of the example was by this was this line follower that was demonstrated with Spinnaker, and a vision sensor that was inspired by the biological retina, where and the interesting thing with this was that it can accommodate a very large dynamic range of input samples. So with this particular group, I believe from UK, was able to show was able to demonstrate a line follower robot by interfacing it with the silicon retina based sensor, and also process the samples in a Spinnaker test board, which implemented a spiking neural network, and then give the output to the actuators of the robot. And another interesting thing that people have been doing is, looking at the dynamic vision sensor cameras, which are again, spike-based sensors, which where the camera looks at where the image that a camera captures is basically like given the camera outputs events corresponding to the changes in the images where it is being focused. So people have demonstrated different applications, and one of them, interesting ones, is where people can play rock paper scissors, where it identifies the different gestures that the human hand is making in front of the camera. And so these are some of the interesting, fun applications. Also, in order to further the development of algorithms, that is algorithmic benchmarking, there are several data sets that people have come up with, and one of where with these neuromorphic sensors, and one of the prominent ones is the neuromorphic MNIST dataset, which is a which converts the traditional MNIST dataset into a spiking version, or it's also termed as the address event representation format, where the digits are converted into spike format by showing it through a dynamic vision sensor camera. And in terms of the audio applications, also there have been a certain number of demonstrations with neuromorphic hardware. And one of the most prominent one was the one on the Loihi hardware, where where the primary goal was to study the power consumption, but they were able to get uh, uh, almost the same accuracy as a traditional neural network on an SNN implemented on the Loihi, the Intel's Loihi platform, with much less energy consumption compared to the other, edge hardware systems that are out there. So the problem here was to identify the different keywords that are being spoken, and the data set that they used was the Amazon Mechanical Turf dataset, and they were able to achieve roughly the same. I think the best case was 93% accuracy, which was the same for both the ANN and the equivalent SNNs. And another so this the keyword. Sorry for the typo. I think there's it should be keyword spotting application on Loihi. So another application was with the neuromorphic auditory sensor, and Spinnaker was to classify the was to make a classification of the pure tones that are generated by by a standard MATLAB program. So this was mostly like a demonstration of both the neuromorphic auditory sensor, which is modeled based on the human the cochlear principle, where which can accommodate again a high dynamic range of the audio intensity. And then the Spinnaker, which implements the spiking neural network, can perform the classification of the different frequency bands that are that is there in the input audio signal. So this is some of the cognitive applications that people have demonstrated. This just a very hand-picked samples from the vast set of applications that are out there. So now I'll go deeper into what are the evolutionary algorithm and evolutionary algorithmic work that that we have that our group has done at the lab, and also some of the algorithmic work that I've been part of. So one of the most prominent evolutionary algorithm for spiking neural networks is the EONS, or the Evolutionary Optimization for Neuromorphic Systems, which was developed by my mentor Catherine Schuman. I believe she would be, if she is a speaker here, she can delve much further deeper into this. But on a high level, what it does is that we start with an initial a random initial state, which has multiple networks, multiple spiking neural networks that are randomly generated and randomly initialized with their both with respect to their topology and as well as with respect to their parameters, which include the synaptic weights, delays, neuronal thresholds, and leak parameters. And then so the way it proceeds every generation is that each of the networks in a population is evaluated by passing the input data sample, and then we select the parents for the next generation, apply certain genetic operations such as mutations and crossovers, and then the offspring population is now part of the new generation. So the benefit for that this particular algorithm offers us that it can co-optimize all the different parameters, whereas the previous learning algorithms that we looked at, they were able to optimize only one or at the max two parameters, and primarily weights were the only parameters that would be optimized. But here we can coherently optimize all the different parameters of the spiking neural network, and also for a given task at hand. So with this, the EONS can produce SNNs with very sparse connectivity, and it's very useful for a co-design effort where you're trying to optimize the network parameters for a given underlying hardware, and also it can potentially evolve the underlying the design for an underlying hardware as well. However, the drawback to this is that it can be slow to train because we'll have to evaluate multiple such networks in parallel, and it works well only when we have a very a large set of computing resources at your disposal. And also and this has, and because of this, it can operate on like a very small set of problems, whereas if we scale up the problem size or increase the input dimensionality, then it becomes a challenge to train the network for a given for that large scale problem. So at our end, we have done certain preliminary studies for different applications, and so another evolutionary algorithms that we are looking at ORNL. It's again from the traditional evolutionary algorithm domain. It's a general purpose EA, which is called the LEAP framework, the library for evolutionary algorithms in Python. So this particular framework, which was developed by Mark Coletti at our lab, it can evolve. It can basically optimize different parameters of the network. But however, the topology of the network has to remain fixed. And this and since it's a general purpose evolutionary algorithm, it can be applied to both ANNs as well as SNNs. So we have also shown it to be applied to SNNs in terms of optimizing the weights, delays, and thresholds of the network. And as another modification that we did to this particular evolutionary algorithm was look at an asynchronous evolutionary algorithm where we don't wait for the evaluation of the network to complete before starting the where basically we don't wait for all the evaluating populations to complete before starting the next generation of evaluation. Rather, in the asynchronous EA, depending on which of the populations has finished early, that can basically be chosen as the parent for the next generation. So this has been published in the UKCI proceedings in the last year. So this particular asynchronous EA, which is called selection while evaluating, is interesting in terms of control problems, where we don't know where different solutions may take different times to where different networks may take different times to evaluate, and it saves on the overall runtime of the the evolutionary algorithm. So we were able to show that there was roughly about 2x improvement in terms of the takeover times or the convergence time for this asynchronous EA with the selection while evaluating strategy. So coming to some of the applications that we have looked at in with the evolutionary algorithms, So this was mostly from an exploratory or a feasibility study point of view. One of the applications was to look at, can we do state prediction in a solar power plant? And this was done in collaboration with a few folks at the uh, energy uh, energy science department at our lab. So the problem uh, was to look at the different given the solar power plant controller. We need to intelligently predict the states for this particular unit. And the input samples consist of the different voltages and currents and internal signals. And again, they are time series data. We initially saw we started off by looking at this problem as a classification problem and applied EONS to it. So the problem is like we have different sets of X, Y, the input samples, and then the Y, that is the data to be predicted. So looking at certain window of the input samples and the previous window of the output samples, we need to make a prediction of the next state value. So with EONS, we basically with as a classification approach, we were basically training the network to predict the different bins of the output samples. And on this particular data set, we were able to achieve roughly about 79% accuracy. Uh, of course, it's not the best, but we can show that with a spiking neural network of roughly about 800 neurons and 1,000 synapses, we were able to achieve, we were able to accomplish this task with a certain, accuracy levels. And as a comparison, we also applied what is called the decision tree framework from the scikit-learn library. And with a depth of 12, we were able to achieve a classification accuracy of about 91%. And now we also have, a frame in the Neuromorphic 10 lab framework. We also have a mechanism to convert the decision tree that is trained by the scikit-learn library into a spiking neural network for the neuromorphic hardware implementation without any loss in accuracy. And one of the most recent problems that we are currently looking at is again, it's a scientific application where we are looking at EONS and trying to perform a regression. So this is one particular problem where we are collaborating with the group from Fermilab, where they're looking at detecting pixels from the high energy physics experiments. And because of the large volume of data that is being generated by the large scale LHCs, the CMS experiment at the Large Hadron Collider. The goal there is to be able to reduce the size of the data or get the most critical information from the sensory or the charge values that is being detected by the sensor. So for this particular science problem, we are again looking at the evolutionary optimization, but now instead of performing classification, we are performing a regression where the input would be the charge values from the sensor array, and the SNN is trained by EONS to output the different the location and the angle information that are needed from the charge values of this sensor array. And for this, it's currently it's an ongoing project. I don't have the results from it right now. So here the idea is to be able to convert the spike trains that are coming out of the SNN into a real valued, and then use that as a and then compare that with the target to define the fitness function for the EONS to evolve the spiking neural network. So yeah, these are some of the applications that we are currently interested in and are currently working towards it. So yeah, that now concludes the overview of neuromorphic computing research that we are doing at our lab. So to summarize, we looked at the different event-driven learning with neuromorphic computing, which is interesting for on-chip or realizing it on an on-chip neuromorphic hardware, and and we also looked at the different evolutionary algorithms where we can co-optimize different parameters of the network, including the network topology, which is a very hard thing to decide a prior hand. So there is a great potential for broadening the applicability of such evolutionary algorithms with SNNs, and and we also saw that there is a scope to implement a lot of these cognitive and scientific applications with spiking neural networks on low power neuromorphic hardware. And going forward, some of the future directions that have opportunities are like co-designing both the hardware and algorithms with novel materials. And we are also working towards one of the projects with several collaborators at our lab. And another and as I mentioned that while we do have like a neuromorphic software ecosystem, it is there's an opportunity for looking at very large scale ecosystems that can implement any large scale applications, especially with can we have a software ecosystem or a simulator that can basically run seamlessly on different different computing platforms, from simple edge hardware to the supercomputer as well, depending on the scale of problems that we have at hand. So yeah, that brings to a conclusion of my talk. And yeah, these are so I would like to thank my collaborators at the Oak Ridge National Lab and the Neuromorphic Group at the University of Tennessee. So yeah, that brings to an end of my talk, and I would be happy to have any questions if there is time.